Hi everyone, let us consider a typical problem on mechanics. Here we have a uniform rod placed between two spinning rollers symmetrically, which are separated by a distance of small l. The friction coefficient between the rollers and the rod is mu, and we need to find the time period of the small oscillations, or the omega, right? We do have the figure for the situation. And for the small oscillations to take place about the horizontal line, we'll have to displace the plank or the rod by a distance of, let us say, x. So the moment we displaced it, the moment the center of mass shifted as well by the same linear distance. Analyzing the forces, we have normal reaction upwards and the weight down. Now, friction is wherein the ambiguity lies, because we are not aware of the direction of friction. I want you to hear me out and imagine this. The moment we start displacing the plank by a distance x, the normal reaction N2 is now no more equal to N1. Rather, it is greater than N1 in terms of magnitude. This is because of the shifted weight, which is getting shifted towards the point of contact of the roller B and the plank, resulting in a greater M2 than it was earlier before. Now what will happen is, the roller B, in order to perform pure rolling, will oppose this new change of the plank with the help of a friction F2, while the roller A, which is already deficit of the normal reaction, will somehow support the motion of plank with F1. The restoring force, we have F1 minus F2, or mu times N1 minus N2. Right? Now the problem lies in calculating the value for N1 and N2. N1 and N2 can be calculated by establishing the rotational equilibrium. That means tau A has to be equal to 0, and so is going to be tau B. Since the rod is in both translational and rotational equilibrium, so we're going to have this equality hold true. So tau about A will give us a relation between mg and N2. Tau about A will be given as mg times L by 2 plus x minus L times N2. This thing has to be equal to 0, and tau B has to be mg times L by 2 minus x minus L times N1 has to be equal to 0. So we have the value of N1 and N2 derived from the above relations, and plugging in the value of N1 and N2 into this relation, we had restoring force as F1 minus F2, which means mu times N1 minus N2, giving us a net of mu times mg over L by 2 minus x minus L by 2 minus x. It is clear that L by 2 and L by 2 cancels away, and mu mg by L minus 2x is the relation we were working out for. So we have ma as this quantity, and m cancels out, so we have A as minus 2 mu g x by L. Comparing this part with A is equals to minus of omega square x, where omega is the angular velocity of the phasor for the SHM of the restoring force. So we have the value for omega as root of 2 mu g over L, giving us a time period as 2 pi root L over 2 mu g.